So therefore, what you get? So this A inverse composition A to the power n, it gives you A inverse composition identity. So what does it implies? It implies that A to the power, in that case, A inverse composition A. So just you can cancel out A inverse and A. So that means this power will be reduces by 1. So A to the power n minus 1 will give you A inverse. So like this, if you just compose A inverse n times, in that case, what you get? You get A inverse to the power n on the right hand side and that identity element in the left hand side. So therefore, A to the power A inverse whole to the power n, it gives you A to the power n whole inverse and it gives you an identity element. Okay. So therefore, it is clear that if order of A is n and n is the least positive integer, in that case, that n is also the least positive integer for which A inverse to the power n is identity element, and therefore order of A is equal to order of A inverse. Okay. Also, you can show that if order of any element is just infinite, that means you can't get any positive integer, show that or A to the power n is identity. In that case, you can't get any actually positive integer for which A inverse to the power n is identity. Okay. So can you hear me?
Yes, sir. Yes.
Okay, okay,
Yes,
okay.
sir.
So okay, okay. So therefore, so it is the procedure. So therefore, order of A and order of A inverse are always same. Okay. So okay. So let us come to our next theorem. Okay. Okay. So let us come to our next. So now our next theorem is, if A is any element of the group G whose order is n, in that case, if have A to the power m is equal to E, in that case, n must be a divisor of n. Okay, so A to the power m is identity element if and only if n is a divisor of m. So we have to, what we have to prove? So if order of any element A is n, in that case, n must be a divisor of m, where A to the power m is identity. So first, let n is a divisor of n. So what we have to prove? We have to prove that A to the power m is identity. Okay, so it is if and only. So that means A to the power m is identity implies n is a divisor of m. Similarly, n is a divisor of m implies A to the power m is identity. So our first case is n is a divisor of. So if n is a divisor of m, so in that case, m is equal to n into some integer. N is a divisor of m. M is an integer. So therefore, m is
Yes.
equal to n into some integer q. Okay. So order of A is n. So therefore, it is clear that since order of A is n, A to the power n is identity. Now, A to the power n is identity means A to the power m. M is n into q. Now, since m is n into q, we can write A to the power n q. A to the power n q means A to the power n whole to the power q. And therefore, it gives you identity element. Since A to the power n is identity. So if you compose identity element q times, so in that case, you can get your identity element. So therefore, if n is a divisor of n, in that case, A to the power n must be the identity element E. Now, if n is not a divisor of n, so in that case, by division algorithm, we can write m as n is equal to n into q plus r. So since m is equal to n into q plus r, in that case, that 0 less than r less than n, this r is the remainder, and r can't be 0 here because n is not a divisor of n. It is assumed. So therefore, the remainder can be 1, 2, 3 up to n minus 1. Okay. Now, since r is not equal to 0, in that case, a to the power n is identity. What it gives? So the first proof is n is a divisor of m. We have shown a to the power n is identity. Now we assume a to the power n is identity. What we have to prove? We have to prove n is a divisor of m. So a to the power n is identity. Now it gives you a to the power nq plus r. Nq plus r is m. So nq plus r is identity. So we can write it as a to the power n whole to the power q composition a to the power r is equal to e. Now a to the power n is what? E. So a to the power n is e means e to the power q composition a to the power r equal to e. Now e to the power any integer is again e. So therefore a to the power r is equal to e. But which is impossible. Why? It is impossible since r is strictly less than n. That means r can be 1 or 2 or 3 up to n minus 1. And we already know that n is the least positive integer for which a to the power n is identity. So therefore, it is clear that a to the power r can't be the identity element, because in that case, r will be the least positive integer. Since r is less than n, so a to the power r equal to e, it gives you r is the least positive integer such that a to the power r is identity. So therefore, it is impossible. We can't assume r as a non-zero element. So therefore, r must be 0. Okay, r must be 0, and therefore our assumption is wrong. Our assumption was that n is not a divisor of m. It is wrong. So therefore, n must be a divisor of n. So therefore, a to the power n is identity if and only if n is a divisor of n. So a to the power n is identity implies n is a divisor of n. Similarly, n is a divisor of n implies a to the power n is equal to identity. So this is the theorem. Okay. So this is another important theorem. So next theorem. If A is an element of a group G of order n and P is prime to n, in that case, order of a to the power n, order of a to the power P is also n. So this is the theorem. So now order of A is n. Order of A is n, which gives you a to the power n is identity. Now we have to show order of a to the power P is n. How? Now a to the power P whole to the power n. What we have to show? We have to show n is the least positive integer so that a to the power P whole to the power n is identity. Now a to the power P whole to the power n, it gives you a to the power n whole to the power P. So therefore this gives you identity element. So it is very much clear that n is the least positive integer so that a to the power P whole to the power n is the identity element. And therefore it is clear that if P is prime to n, in that case, you can easily say that a to the power P is of order n. If P is not a prime, not prime to n, that means it is not a co-prime of the number n. So what is the case? In that case, you can see that if P is not co-prime to n, in that case, the separation of P and n will be difficult. Okay, say if you consider two integers, say 4 and 8. In that case, a to the power 4 whole to the power 8, it will be quite difficult to handle that a to the power 32, because in that case, that separation, that how much n will be considered, what is the value of n to be considered, it will be difficult for us. And in that case, that P is prime to n, we have to assume that. Okay. So otherwise, the order of a to the power P will not be n. Okay. So this is the theorem. So there is an example. So let y be an element of a group G and order of y is 40. Find the order of y to the power 8. Okay. So we have to find the order of the y to the power 8, where this order of y is given as 40. Okay. So order of y is, since order of y is given as 40, so it is very much clear that that uh, this actually this will be y. This is a mistake. There is a mistake. So this is actually y to the power 40. So y to the power 40 is the identity element. Since order of y is 40, so y to the power 40 is the identity element. Now y to the power 40 is the identity element means, order of y to the power 8, we have to find it. So order of y to the power 8. So say order of y to the power 8 is m. So therefore y to the power 8m must be e. Now clearly, since y to the power 40 is e, in that case that 8m must be 40. So 8m must be 40. Okay, since y to the power 40 is identity and y to the power 8m is assumed to be identity, so therefore 8m will be 40. So 8m will be 40 means, so therefore that okay, let us remove these annotations. Okay, in that case, that 8m is 40, that means m is what? 5. So it is very much clear that order of y is 40 means order of y to the power 8 is just 5. 5 is the order of y to the power 8. Okay, it is a very simple example. So in a group G, order of an element is now 30. We have to find order of a to the power 5 and also a to the power 18. So since order of a is 30, a to the power 30 is identity. Now a to the power 30 is identity means, so this a to the power 30 is e. Now order of a to the power 5 is say m. In that case, a to the power 5m is identity. Since a to the power 5m is identity, so 5m must be 30. A to the power 30 is identity. A to the power 5m is also a to the power 5m is identity. So therefore 5m must be 30. So m will be 6. Okay. So we are done. Now similarly, a to the order of a to the power 18. So order of a to the power 18 is say p. So therefore a to the power 18 into p is identity. So actually 18p must be a actually it will be some actually integer into 30. Okay, it is a multiple of 30 because a to the power 30 is identity and a to the power 18p is now e. So therefore 30 must divide this 18p. So just using our previous theorem. Okay, why? Order of a is here 30 and a to the power 18p is identity. So therefore 30 must be a divisor of 18p. So therefore 18p is must be 30 into q for some integer q. And it is possible only y p is 5. Okay, so p is the least positive integer. So the value of p will be 5. So 5 is the least positive integer for which 30 divides 18 into p. Okay, so therefore that order of a to the power 18 is 5. So it is very much clear also. So, okay. 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 So let us come to our next problem. So if G is a group and A, comma B belongs to G such that A to the power 4 is identity and AB equal to B square, we have to prove that A equal to identity element. Okay. So AB is equal to B square. So actually, if we multiply A square on the left hand side for both AB and B square, in that case, that if we multiply A square on the actually on both sides. Okay, so A B A square will be B A square A square. So A B A square is B A square A square. That means B A to the power 4. Now A to the power 4 is given as identity. So that means it must be B. B A to the power 4, A to the power 4 is identity. So A B A square must be B. Now A B A square is identity. This is B. Now AB is B A square. It is given. So AB is B A square. So in place of B A square, what we have to prove? We have to put that AB. Okay, so in place of B A square, we have to put that AB. So that means what you get? We get AAB is equal to B. So that means AAB is equal to B means A square B is equal to B. So we can just cancel out B from both sides by right cancellation law. So therefore A square must be identity. So now A square is identity. So therefore AB is B square. So AB is B square means AB is equal to B A square. A square means identity. So therefore AB is B composition E. So it gives you AB is equal to B. So similarly, by using right cancellation law, again we can show that A is equal to identity element. So therefore, if A to the power 4 is identity and AB is equal to B square, in that case, A must be the identity element E. Okay. So now let us come to our next portion, which is subgroup. So a non-empty set H is said to be a subgroup of group G if and only if H is itself a group under the operation O. So actually just like subset. So a subgroup is nothing but a subset, okay, of a group. So actually, if you consider any group and if you get a subset of that group, which again forms a group under the actually mother operation O, in that case, that non-empty set H, comma O, this is called the subgroup of the given group G. Okay. So now next theorem, a non-empty subset. It is a theorem. Actually, how can we show that a subset of a group is a subgroup? So there are two conditions. So a non-empty subset H of a group G forms a subgroup if you consider any two elements A and B from H. In that case, that composition element A composition B must belongs to H. Similarly, if you consider any element A belongs to H, in that case A inverse belongs to H. Okay. So it is a theorem. So these are two conditions. If these two conditions are satisfied, in that case we can actually say that H is a subgroup of the group G. Similarly, a non-empty subset H of a group G, this forms a subgroup, okay, of H if and only if A comma B belongs to H implies A composition B inverse belongs to H. So actually instead of these two conditions, we can use only this one condition to show that any subset of a group to be a subgroup of a group G. Okay. So if we have any non-empty subset of a group G, in that case, to show that non-empty subset H to be a group, we have to just satisfy this one condition, that if you consider A and B, these are two elements from the subgroup H, and in that case, A composition B inverse must belongs to that H. Okay. Now, next one is intersection of two subgroup of a group G is again a subgroup. So it is very, very, very simple. So let us consider any two subgroups of a group G. So it is very much clear that any subgroup means it is a group actually. So therefore there is an identity element, and since it is a subgroup, it contains the identity element of the mother group. Okay, so that mother group is G, and if E is the identity element of G, And since we have already shown that the identity element of any group is unique, so that means H1 and H2, if these are two subgroups of the group G, in that case, identity element must belongs to this H1 as well as H2. So therefore, E belongs to that H1 intersection H2. So since intersection contains this at least one element identity, in that case, it is non-empty. So H1 intersection H2 is non-empty. Now, what we have to show? We have to show H1 intersection H2. If this non-empty set is just a subgroup. Okay. So now let us consider two elements, A and B from H. Okay, H1. So sorry, A comma B belongs to H1 intersection H2. So let us consider two elements A and B from this intersection H1 intersection H2. So therefore A comma B must belongs to H1 as well as A comma B must belongs to H2. Now we have already assumed that so this H1 is a subgroup as well as H2 is a subgroup. So therefore A comma B belongs to H1 must implies A composition B inverse belongs to H. Similarly, A comma B belongs to H2 implies A composition B inverse belongs to H2. So therefore, it is very, very much clear in that this A composition B inverse belongs to H1. This will be H1. So there is another printing mistake. This is the H1. Okay, so this will be H1. So that means A composition B inverse belongs to H1 as well as A composition B inverse belongs to H2. So therefore, A composition B inverse is the common element of H1 and H2. So therefore, A composition B inverse belongs to H1 intersection H2. Okay. So therefore, H1 intersection H2 is a non-empty subset. Okay. So therefore, this is a non-empty subset of, sorry, a non-empty subset which satisfies this condition that A comma B belongs to H1 intersection H2 implies A composition B inverse belongs to H1 intersection H2. So therefore, H1 intersection H2 is a subgroup of the group G. And we can show that union of two subgroups may not necessarily a subgroup. So if we consider the group Z plus, this Z plus is a group. All of you know that Z plus, the set of all integers with respect to addition operation, is a group. If you consider 2Z plus, so that means these are all the integers which are multiple of 2. And let us consider another group which is a multiple of 3, that means 3Z plus. So 2Z plus, 3Z plus, these are two subgroups. So actually union is this. So 0 plus minus 2 plus minus 3 plus minus 4 plus minus 6. So that means we have to consider all the elements of 2Z plus and 3Z plus. Now, it is not a group. This union is not a group. Why? Because 2 and 3, these are elements of H1 intersection, H1 union H2. Because 2 belongs to H1 as well as the 3 belongs to H2. So that means 2 and 3, both are elements of H1 union H2. But 2 plus 3 is 5. 5 doesn't belong to H1 union H2. Why? Because 5 is not a multiple of 2, not a multiple of 3. 5 is neither a multiple of 2, not a multiple of 3. So therefore, 5 doesn't belong to H1 union H2. So therefore, H1 union H2 can't be a subgroup. Okay, it can't be a subgroup. So therefore, we see that intersection is always a subgroup for any two subgroups, but union may not be a subgroup for two subgroups of a group. Okay, so therefore, it is necessary to actually mention some properties. So